So we've seen that exponential growth functions are unrestricted, or they don't have a limit. So as x goes to infinity, or independent variable, our function goes to infinity, positive infinity. But in real world, populations often have a maximum values. Often they slow down at some point and start tapering off. Or we can call this a maximum sustainable population. So how can we model this? Well, if you remember from section 3.1, we had logistic functions. So logistic functions are the form c over 1 plus a times b to the x. So we see our exponential function, but it's put into a ratio. Or we can also model that, since we can model every a times b to the x as a times e to the kx. We can model this as c over 1 plus a times e to the negative kt. So looking at example 4, we're given a table of the population of Florida and Pennsylvania over the 20th century. So how can we model this? Well, we've used tables like this before, and we created regression models. So what you're going to do is you enter a spreadsheet, enter these values. So you can start with 0 for 1900 and ending with 100 for 2000. And then for the population, just enter these values. These are in millions. Then you would go to your menu and create a logistic regression. And for Florida, you should get something like this: 28.021 all over 1 plus 9018.63 times e to the negative, and I'm going to write k over here since this is such a large number, 0.047015, and then times t. So then you can use that to find the population over different years, starting with 1900 as 0. And what would the maximum sustainable population of this be? Of Florida, it would be. In this case, it would be the 28.021. So 28 million would be our maximum population of Florida. So we can go over this more in class when you actually have a calculator. But the principle is pretty simple. Just entering your data into a spreadsheet and then creating a regression model. In this case, a logistic regression model.